Well, applications today. We want to do one thing. We want to use the law of sines and law of cosines to solve applied problems. And we're just going to use properties of triangles to do that. Now, there's obviously no limit to the number of situations that could arise. We're just going to look at a few sample cases. So let's jump right in. We have ourselves a lake. We want to know, well, pond. We better go with pond here. A little pond. And we can use a transit. This is one of the principles that is used to measure inaccessible distances. We would set a transit at the left edge of that triangle that's formed. We can use the transit to measure distance, such as the 392. We could also measure the distance 416. I'm going to show you how to do that over the next couple of days. And then we could measure the angle in between, which turns out to be 27 degrees 15 minutes. We want to know how wide the lake is. Okay, that's what we're looking at. So, the first thing that we really need to do is we need to take that angle and convert it into pure decimal degrees. How are you going to take that 2715 and convert it into decimal degrees? Divide by 60. So 27 degrees 15 minutes becomes what? 0.25. 27.25 degrees. We just want to find that distance across the lake. And so this one's pretty straightforward. What are we going to use to find that distance? So it's a side angle side scenario, so you're using law of cosines. So our opposite side, which in this case will be x squared, is going to be equal to the left side of our angle, 392 squared, plus the right side squared, that's 416 squared, minus 2 times the left times the right times the cosine of 27.25 degrees. A little calculator work there. You probably pretty good at that after your homework from yesterday. If you do that, I'll give you just a minute to crunch that out. Let me know what you come up with here. 191.76 is what you should get. All the dimensions we were given were rounded off at the nearest foot, so it's only reasonable to do the same, and so our distance will be 192 feet across that pond. And that's that. Okay. Different scenario. We've got part of the purpose of this problem is to work with the terminology just a little bit. If you've ever been on top of Grandad Bluff, you know that when you look out Grandad Bluff towards La Crosse, you look right down Main Street. And you can see the intersections, the major intersections, pretty well. So we're going to assume a couple of things here. One, when you look from Grandad Bluff down, the nearest major intersection you see is the intersection of Losey Boulevard, Main Street and Losey Boulevard. So if you stand up here and look down to the intersection of Main Street and Losey Boulevard, you will see I'm going to modify my drawing just a little bit here. We can measure that angle of depression. That is how many degrees down from horizontal we have to look in order to see that intersection. It turns out that it is 15 degrees. Now, this picture isn't quite to scale, but there's a horizontal line. That means this angle measure is 15 degrees, which would be a lot more flat than my picture, but oh well. Okay, and you can look off further into the distance, and from Losey over to West Avenue is 12 blocks. Losey is basically on 24th Street. West Avenue is essentially 12th Street. So if you look further off in the distance, you see the intersection of West Avenue and Main. And that will, because it is further away, not have as great of an angle of depression. You're only going to have to look down roughly 4 degrees to see that. Now, it's not exact. No city is exact, but you can roughly figure, whether jogging or riding your bike otherwise, you can roughly assume that there are 10 city blocks to a mile, give or take a block. Okay, well, there's 5,280 feet in a mile, so divide that by 10 blocks. Each block, minus the width of a street, somewhere in the neighborhood of 500 to 550 feet for an average city block. We're just going to assume that every city block is 500 feet. So if it's 12 blocks between Losey and West Avenue, what's the distance in feet here got to be? 12 blocks times 500 feet, there will be 6,000 feet. A little over a mile. And the question is, how tall is Grandad Bluff? How far above the street level are you? Well, there's a few different ways you can go about this, but ultimately, I would just want you to look at the triangle. That does define a triangle, right? You know several angles here, and you know one side, so that does define a triangle. We ultimately just need to figure out how high above the base the peak of that triangle is. That'll be the height of Grandad Bluff. Now, you started spotting some angles. You know all 3 of them based on the information given. What's this angle up here got to be? This angle is going to be 11 degrees. That's right. Okay? You know more of them. What's this angle down here going to be? That's 4 degrees. The angle of depression from up there is going to be the same angle of incline from down here. If you're standing down here, hopefully not in the middle of the intersection, but near the intersection of West Avenue and Main looking up at Grandad Bluff, you're going to have to look up 4 degrees. The same is true for the near intersection. If you have to look down 15 degrees to see it, if you were standing down there, you'd have to look up 15 degrees to see it. So over here you'd have 15-degree angle of incline, which means that the interior angle here is 165. You can also see that by subtracting 180 minus 11 minus 4. So either way, we know all the angles within that triangle. No, that doesn't answer the question. All that does is tell us all the angles in this triangle. What dimension are you actually looking for here? You want to know the altitude, we'll call that x. That's what you're really looking for here. Now, how can you find that? Okay, we know that this will be a right angle. That's true. I think it's the same thing you were saying. You got to find one of these other sides. Now, this is the convenient one to find because you can find this one since it's the side of our blue triangle. And once you know this one, it's the hypotenuse of the right triangle. Okay, so we're going to solve this triangle in order to get information about this one. So what are we going to use? Let's call this value here h for hypotenuse. Okay, let's find h. Which law are you going to use to find h here? Sines, because we know all 3 angles. We know angle, side angle, and this one. So h, to find h, we know, let's see, what's our opposite pair? We know 6,000 feet and 11 degrees. So we know that. I'm going to do that over here. The sine of 11 degrees over 6,000 feet is equal to the sine of what? 4 degrees over side h. Solve that, and you'll find that h is equal to. Now, even though our information given was, or we rounded off to the nearest foot, we're going to leave at least 1 decimal place until we're done with the question. Then we'll round back to a foot, but don't round too early. 2193.5. So it's about 2,193 feet from Grandad Bluff down to that intersection. Well, now we're home free. Now we're going to go use a little right triangle trigonometry. What trig function are you going to work with in your red right triangle there? You have more than one choice, but the easy one is to use this as your angle reference. Sine of 15 degrees is going to be your opposite side, which is the one that we want, x, over the hypotenuse of 2193.5 feet. And a minimal amount of algebra there will tell you x equals .568 feet, and we're done. So we got to get information about our oblique triangle to have enough information about the right triangle. Aaron. We've got a roof truss here, a scissor truss actually, type that would be used for a vaulted ceiling. We want to find what that angle B is in the corner of that scissor truss. What's the first thing you got to do here? Before you do any math, you know you're dealing with what, you can throw out all the unnecessary parts of that truss, simplify it down to a triangle, and what's the scenario you're dealing with? Side, side, side. The problem is the dimensions it's given in are all mixed up. You should get them in either all in feet or all in inches. Either way, it doesn't matter. Let's put them all in feet just for the practice here. 10 feet 4 inches, we'll leave plenty of decimal places. Let's leave 4 decimals. 10 feet 4 inches becomes 4 divided by 12 is 1/3, or 10.3333 feet. Three feet 6.5 inches. 6.5 inches, 6.5 inches divided by 12. 3.5417. And the bottom member, 8 feet 7 1/4 inches. That's going to be 7 1/4, 7.25 divided by 12. 6042. Everybody agree with those measurements in feet? Either one would be equally accurate as long as you leave enough decimal places. Okay, well from there, there's not much to do other than apply the law of cosine. So we know that our opposite side from the desired angle B .5417 squared equals subtract off the square of 10.3333 and square of 8.6042. Work all that out into cosine of beta when you solve for cosine b, actually. Cosine b turns out to be 0.94627. And one more step tells you your angle of 18.9 degrees. 18.9 degree angle down in the corner there. We've got another bolt circle problem here. We've got a bolt circle. The diameter of the bolt circle is 4.5 inches. We want to know how far it is between any two bolts. Well, where do you want to complete your triangle? We know we need a triangle in there somewhere, and one side of it better be that distance. If you connect the two radial lines to those two bolt holes, you end up with a triangle. We know a whole bunch of information about that triangle. It's one thing we know about that triangle. Exactly. The two side lengths are radii of this circle. So the radius is 2.25. Okay, we need at least one angle. Yep, we know that that central angle is 144 degrees because 360 divided by 5 bolts means there's 72 degrees between each bolt hole. We've got 2 of them there, so that's going to be 144 degrees. 2 times 72. Well, then we're set. Law of cosines. The opposite side is our distance x. Yep, if you were to look at this angle, it would be 72 degrees, and that angle would be 72 degrees, so then your total included angle is 144. Law of cosines, there it is again. There, the left and right sides are the same, and so minus 2 left right is really just minus 2 times 2.25 squared. What? Huh? This is going to be 2 times 2.25 squared. This will be 2 times 2.25 squared times the cosine of 144. So these don't cancel each other off of there. This has got the cosine of 144 attached to it. So you still got to crank that out. You could simplify it, but the simplifying is more trouble than it's worth. You should end up with, go to the nearest thousandth, 4.280 when you round it off to the nearest thousandth. 4.279 something rounds to 4.280. And we're done. That's our distance x. Here's what we've got, a 385-foot tall tower sitting on a sloped hill. Slight grade to this hill of 4.6 degrees with horizontal. We know that the tower is 385 feet tall. And what else do we know here? We know 490-foot guy wire, support wire, anchors the tower on the south slope. So we're going to have a wire up here. That is 490 feet long. Okay, well, we want to find the distance from the base of that tower down to the point where the cable's attached. So we're going to look for distance D there. Now, we do know a little bit about that, the angles in that triangle. We know two sides, of course. Do we know this angle? We don't, because we don't know anything about the angle of that wire. Do we know this angle? Same problem. But do we know this angle? We do. If that thing was sitting on level ground, what would this angle be? 90 degrees. But the ground is sloped 4.6 degrees, so what does that do to the size of this angle? Makes it 4.6 degrees larger. This side would be 90 minus 4.6 degrees. This side is 90 plus 4.6 degrees. So this angle is 94.6 degrees. All right, well, now we've got a side set angle. This is the ambiguous case, but the beauty of the real world is that ambiguous case doesn't show up because we know what we've got here. The only question you need to ask yourself is this cable going to be long enough? Just look at your picture. If you have a 385-foot tall tower, will a 490-foot long cable be long enough to attach somewhere? Sure it will. What's the minimum length for your cable? 385. It has to reach the ground. And it has to be a little bit longer to move away from the base of the tower. Now, it's not going to do much good if this cable is only 386 feet tall because it's only going to be a little ways away from the tower, but 490 is plenty. So we just need to solve it. There's no ambiguity here. There's no question about it. There can only be one distance here. We know it's long enough. We're good to go. So we're going to use law of sines. This is the pair that we know, sine of 94.6 over 490. Equals what, though? Yeah, we only have one choice. Even though it's D that we're looking for, we don't know the opposite angle. If we knew this angle, then we could solve for D, but we don't know either of these two, so we can't jump to this pair yet. We have to work with this pair of opposites. So we do know that we can, let's call this angle down here theta. Okay, so we do know that this will be the sine of theta over 385. Solve that, and you'll find that theta is 51.55 degrees. The reason I'm leaving an extra sig dig, is that the answer to the question? No. We're just going to use that to find the answer to the question later. So leave more decimals than you will on your answer if we're going to have it. There's no point in rounding too much while we're still working. Okay, well now we're set to find this angle up here. We'll call that angle alpha. And by subtraction, alpha is going to be (180) minus the two angles that we know leaves us with a remainder of 33.85 degrees up there. Now we can answer the question. The side that we want to know, D, over sine of 33.85. This is the angle pair we're working with. So d over sine of 33.85 degrees equals, now use the pair that we were given, 490 over sine of 94.6. Notice that this one I put the distances on top and the angles on the bottom. Did that intentionally. You can use law of sines either way. It doesn't matter. And solve this and you'll find out that d is equal to about 273.8. Round it off to the nearest foot like the other dimensions are given to the nearest foot, and we'd have to call it 274 feet long. That distance, it'll be anchored 274 feet down slope.